invitation. I'm very honored to be here. It's always a pleasure to be in Greece. So the title of the presentation is One NumLab memristor on edge of chaos enables small signal amplification in an otherwise dumb analog electrical cell. This is basically the main topic, but I will also briefly touch upon other aspects of the research, because we are working heavily on these devices which show the capability to amplify small signals. And by this capability, they induce interesting properties on the circuits they are embedded into. So let me first acknowledge the collaborators of these research studies, which, as I said, has a wide spectrum of applications. And so there is here a long list of collaborators, starting from Professor Corinto and Professor Gilli from Politecnico di Torino, Professor Tesi from the University of Florence, Professors Di Marco and Forti from Siena, then Professor Ronald Teslav and Demir Kol, Ahmet from the University of Technology in Dresden, where I was working for 11 years. And then Stefan Slezacek and Thomas Mikolajczyk, which work at NumLab, the company that produces these locally active devices. And then we have also long-standing collaboration with the group of Joshua Young and Sally Williams at University of Southern California, and of course with Professor Chua. So in underline is the people that have been working mostly on in the last 15 years. So let us see an outlook of the presentation, motivation, and then we will show how to endow one of these devices with a negative differential resistance, how to stabilize them in a negative differential resistance operating point, where then their signal amplification property can be exploited. We shall also look at some recent results on using these devices for neuromorphic computing circuit design. And then we will look at the recent work on studying how to build small signal amplifiers out of these devices. And we will also touch upon past studies on explaining complexity and especially spatiotemporal pattern formation using devices on the edge of chaos. So these are the physical realizations of membristive devices with local activity property from NumLab, which is a company based in the campus of TU Dresden. And here you see the size of one device, a single device. The company logo is on the right side. So we developed models for these samples. As you can see here, on the left, we have the memristor model, circuit theoretic symbol, the standard one. And on the right side, you see our circuit theoretic model for one sample of this niobium oxide threshold switch from NumLab. And of course, the model, as you can see on the right, involves the mathematical description of the core memristor, which we indicate as M tilde. And it's, as you can see, is an extended memristor because the conductance depends on the state, which is the temperature of the device, and on the input voltage. And then there is Newton's law of cooling, which describes the evolution of the state of the temperature into the filament. Then we have, of course, some parasitic effects, and we'll show shortly how important they are. So we have one resistor in parallel and then one in series. And the resistor in parallel, in fact, is a nonlinear device. It's a nonlinear resistor. And so, of course, the combination of these devices introduces some circuit theoretic constraints. And this is the overall model. And here we see how we reproduce quite nicely the experiments. So here we reproduce under quasi-static excitation of the device. We reproduce the current voltage response. As you can see, it is important to sum the contributions of the various elements. Okay, of course, the current that flows here is the sum of the currents that flow into the two branches. But here, actually, we show how the voltage, the overall voltage of the whole memristor, the composite memristor one port, is the sum of the voltages that drop across the resistor, the linear one, and across the nonlinear resistor. So summing up these two contributions, you have the characteristic, the typical S-shaped characteristic of the memristor. This is for one sample, and then on the right side, we have done it for another sample. But in this case, we consider the sum of the currents, you see. So now, for the same voltage, we need to add, of course, the two currents here to have the current of the composite device. So you see that the addition of these parasitic components allowed us to reproduce an S-shaped characteristic that finally matched the experimental observations. On the left side here, you have measurements and modeling. But you see that how important it is to add sometimes to the core memristor model other parasitic effects in order to match really the experiments. And here is the model prediction of how the temperature in DC conditions varies with the voltage for two different samples. Using this type of models, we have reproduced the complex behavior that occur in neurons and on the basis of the famous Hodgkin and Huxley neuron model in simple analog electrical cells. So for example, this is the model of Hodgkin and Huxley. It's a fourth order model. This is the circuit theoretic interpretation given by Leon Chua, where you see the sodium and the potassium ion channels. In fact, they are not time-varying resistors, but they are memristors. This was the only issue in the model of the Hodgkin and Huxley. They interpreted the channels as resistors, time-varying resistors. In fact, they are memristors, and this is the correct interpretation from Leon Chua, 2012. And this is the famous classical bifurcation diagram. So basically, you can plot here the steady-state stable and unstable behaviors of the voltage across the capacitor versus the input synaptic current. Okay, so you make a sweep of the current from 180 microampere to 0, and you observe all possible behaviors that can occur into the neuron depending on the initial conditions. Okay, so starting from 180, you have this blue curve. It means that there is an operating point which is silent. So the neuron just sits on a stable quiescent steady state. Then there is the first bifurcation, a dramatic change in the properties of the system. In fact, you have an off supercritical bifurcation. The operating point becomes unstable. That's why you have a different color. And then you have the birth of infinitesimally small, almost periodic oscillations in the neuron. And as this is the maximum and the minimum of the voltage across the capacitor for each current. Okay, as you decrease the current, of course the amplitude grows, and then you have a second bifurcation here. Once again off, but it's a different type. It's a subcritical. What means is that you see the operating point returns to be stable. So now the neuron can still return to the quiescent state. But there is the birth of oscillations, once again, which are unstable. Okay, so these curves that you see here, it's very sharp curves, are the maxima and minima of unstable oscillations. So there is the coexistence of attractors. There is a stable operating point here in blue, and there is still the large stable cycle. So the neuron can either oscillate or can go to the quiescent steady state, and this means there is some basin of attraction for the two attractors. In fact, the basins of attractions are separated by the unstable limit cycle. And as you can see, this stability window is very, very tiny. And at some point here, there is a third final dramatic bifurcation, which is a global bifurcation. The two cycles, because as you can see, the unstable is growing very dramatically and in a very short range of the current, and goes to touch the large stable cycle. And so there is basically the collision between the two cycles, and together they annihilate each other. So this is called saddle node limit cycle bifurcation. And finally, the ending result for the neuron is that it is only one globally asymptotically stable quiescent steady state. So after that current, for the third bifurcation, the neuron can only be silent. Okay. So this is the so-called all too known effect. Not to be confused with all or known, which we will see in a few slides. Okay, so basically, just before this bifurcation, there were two attractors. After the bifurcation, there is only one attractor, basically, the known behavior. So the neuron is silent. Okay, so we reproduce actually the same bifurcation diagram using just 3 elements, one capacitor, one memristor that I described earlier on from NumLab, and one DC current source. So this is the model I showed you earlier on. Of course, now we have a new state equation, because for the capacitor voltage, before we had only the state equation for the temperature, there are some circuit theoretic constraints, and this second-order model is able to capture qualitatively the same cascade of bifurcation phenomena that occur in neuron, according to the Auction and Huxley predictions. So it's interesting that we just need a second-order model. Of course, we need a locally active memristor inside this circuit in order to, so it is so rich in dynamics that it can actually compensate for the lack of orders, because the other one is a fourth order, right? The Auction and Huxley is fourth order system because it has a capacitor, it has 2 memristors, of which one is the second order one, the sodium. Here we only need a first order memristor and a capacitor. And these are the parameters. Something has happened? Okay, sorry. I don't know how to delete this window because I don't see it here, but basically this is the parameter set, and this is the bifurcation diagram that is actually qualitatively reproducing the same cascade of 3 bifurcations that occur in the Auction and Huxley neuron model, okay? Here I want to show you another point, which is important. We need to be fair. Of course, our circuit cannot reproduce high-order phenomena in neurons. Then you need to combine neuristors in order to observe them. So if you want to see all these type of spike patterns, then you need to combine a few neuristor cells. For example, here, we show that a 5th-order neuristor, which is a chain of 2 neuristor cells that, as I showed earlier, can reproduce the all or none phenomenon. What does it mean? This is the sub or super threshold response of the memristor. Unfortunately, you cannot see it very well. Maybe I should try to... Wait a second. Maybe I just close the window and let's see. Maybe not. So this is the 5th-order memristor cell. You excite it from the input voltage, right, with a small pulse or with a large pulse, okay? And as you can see, as a result, the memristor, at the output, you either see no response, basically, just a little spike, or you see the typical action potential, like the response all or none phenomenon, okay? Here, however, in order to reproduce this more complex phenomenon, you need some combination of neuristors, okay? So this, for example, is a 5th order because you have 2 second-order neuristor cell and 1 first-order capacitor. And we have done much more. If you want to see this, this is a very long paper where we reproduce all type of spike patterns that can occur by combining suitably different neuristor cells, similarly as Professor Tesla showed earlier on with a long chain of neuristor cells and the generation and transmission of action potential through the axon neuron. So now another topic that we have described, also Professor Tesla touched upon this, is symmetric breaking phenomena in reaction diffusion systems. So this is just one example. Stephen Smale wrote this seminal paper in 1952, if I believe correctly. And basically, he was mesmerized when he saw that 2 identical reaction cells that were silent on their own, they could wake up and oscillate in synchrony when let interact via diffusion processes. And he wrote a paper where he reported this very counterintuitive observation he couldn't find an answer to. We have been able with, when I was working at Dresden, to build a reaction diffusion array made up of two memristive relaxation oscillators combined with a passive resistor, and to observe the same phenomena, okay, in a 4th-order system. Smale was earlier operating with an 8th-order system, but what is most important is also the reproduction of the phenomenon, but we also explain the reason behind the phenomenon. So the reason behind the phenomenon is that each reaction cell is on the edge of chaos. And we have a comprehensive analysis in this paper, if you're interested, where we analyze all possible operating domain for the cell, and we demonstrated that it is not possible to observe this complex emergent phenomena unless the cell is on the edge of chaos. And this is the simulation result. So you can see that Okay, so you can see here that this is the behavior of the uncoupled cell. Okay, is one example from one initial condition, but irrespective of the initial condition, the cell is silent, okay, on its own. And then you couple two of them, and for large values of resistance, okay, you have the so-called homogeneous solution. So both cells, this is the expected solution, right? Both cells, they converge to the same quiescent steady state as in the uncoupled case, okay? But suddenly, when the resistance is decreased, we observe a Turing instability phenomenon. So basically, what happened is that actually we studied the bifurcation behind this phenomenon. We have no time to go through it, but it's a pitchfork supercritical bifurcation. Okay. Anyway, the two cells converge toward two different solutions. And of course, if you extend this to an array, you would see that you form static patterns, the so-called Turing patterns. Okay. And interestingly, decreasing the resistance even further, you have the off bifurcation. Actually, to be more complete, there are two solutions that are born at this. When you have a Turing instability, there are two locally stable solutions that are born, static. And then there are, when the resistance is decreased below a certain threshold, there are two off bifurcations. And so you have the bistability phenomenon, but not anymore in terms of quiescent solution, but in terms of limit cycles. So all these phenomena are only possible if the reaction cell is on the edge of chaos. So it's locally active and stable, according to the interpretation that Professor Tesla explained this morning. So basically, just to conclude, the solution to the Smale problems is the mechanism responsible for the transformation of a stable silent reaction cell into an oscillatory a live reaction cell via diffusion is the edge of chaos condition for the uncoupled reaction cell. Okay. So here, just to repeat, a physical system is said to be on the edge of chaos about an operating point if it's locally active and stable about it. When it's poised on an edge of chaos operating point, the system appears silent, sitting at the quiescent steady state. However, it hides a high degree of excitability, which explains why it may support emergent phenomena, including spatiotemporal pattern formation. It takes just tiny perturbation to its nominal operating conditions for emergent phenomena to appear. For example, we had in the example a supercritical pitchfork bifurcation leading to the static pattern formation. So now let us go again back to the switch from NumLab and explain how to stabilize the devices in the negative differential resistance branch, because this is the branch that we want to exploit for circuit design, basically. All these circuits that we observed earlier, they must ensure that the memristors inside the circuits are operating in the NDR branch, so in the branch of the characteristic with the negative slope. Okay, so basically, the device is a current control device. In fact, when you draw the characteristic in the lab, the whole characteristic is stable. Also, the negative differential resistance branch, only if you apply current. So here we apply 3 currents, and we measure 3. For each current, we measure only one stable operating point. This can be explained with the technique called the dynamic route map. Once you have a model, you just plot the time derivative of the state versus the state for each possible DC stimulus, okay, without going through the mathematics. So for example, here is one example. You fix the current to IS equal to 1180, which is this value here, okay? And you plot x dot as a function of x, and you look at where the characteristic crosses the state axis. This is the operating point for the system, and there is, as you can see, only one operating point per current. Moreover, if the slope is negative, the operating point is stable. And this explains why in the measurements we could observe only one stable operating point for each current. And this is important because we can have a totally stable NDR branch. So the right way to control these devices is in current, but sometimes in experiments it's easier to apply voltages. And unfortunately, with the voltages, one has to be careful. Okay, here it's just once more the characteristic, the DC characteristic under current control. Okay, here again, I plotted the current on the x-axis. You can stabilize the whole NDR under current control, and this is how the temperature, Q stands for temperature in this case, changes with the current. Okay. under DC conditions, okay? Because you can extract not only the voltage current data, but also the temperature data, okay? Under DC condition. These are the ranges of current, temperature, and voltage under which the memristor is on NDR, okay? But if you apply a voltage across the device, the situation is not so nice anymore, because now you see, for example, if you are in the NDR window, okay, you see this voltage, and you consider the load line approach, this voltage can cross the characteristic in 3 possible operating points. So you have 3 admissible operating points. And unfortunately, the one in the middle, the one that is most of interest to us, is unstable. Again, you use the dynamic route map approach. Okay, so as you can see, as before, when the voltage is outside the NDR window, you have only one operating point possible. You have only one crossing, and it's stable. But unfortunately, when you apply a voltage in this NDR window, you have 3 possible operating points. Look, for example, at this red state dynamic route, you see, and the outer operating points are stable, and the inner one is unstable. You can see this also from the arrows. Okay, so basically this point is unstable. The memristor can only stabilize here or here, depending on the initial condition. So we have an unstable NDR branch. Okay. However, there are techniques. I mean, there is a very simple circuit-ready technique to stabilize the memristor in the NDR, even if it's a voltage-driven. It's important to add a resistor, a simple resistor in series. The resistor must comply with a certain condition, inequality condition, but if you want you find the details in this paper. So it's possible to stabilize the memristor in the NDR by using a suitable resistor in series, okay? So sometimes in the experiments, it is easier to apply a voltage, but then you need the resistor in order to use this device in the NDR. Here is the explanation, the results. So basically here, as you can see, you have the DC characteristic. Instead of plotting VM versus IM, we plotted VM versus VS, okay? And these are, for the same value of resistor, 100 ohm, 3 different state dynamic route. You see that each of them, it crosses only once, and with the negative slope, the state axis, which means that we have stabilized the memristor in the point shown with the circle, okay? And in particular, we have chosen the voltages, VS1, VS2, VS3, in such a way that with the resistor of 100, basically the memristor voltage under DC conditions is the same, is 0.998. And these are the 3 points that correspond to the 3 temperature on the x-axis, okay? So these are the 3 points, okay? One, as you can see, is in the positive differential resistance region at low VS. One is in the other PDO region, positive differential resistance region, in the upper part of VS. And one is in the desired NDR branch, which is colored in red, okay? Now we will compare the amplification properties of the cell in these 3 different operating points. So let us see this first case study. So basically we have biased the device with the same resistor and 3 different voltages that poise the device once, 2 times in the PDR, different PDR branches, and once in the interesting NDR branch. And then so the memristor bias point share the same values for VM. I mean, this was just a choice. It is not so important. But then we superimposed a small signal sine wave on top of the DC level. And so we have a small signal sine wave of amplitude very small in order to make small signal analysis later on, and the frequency of 100 Hz. At the moment, we are just doing simulation to experience and explore the behavior. As you can see, when the memristor is in the PDR operating points, the amplitude of the sine wave, now here we are looking only at the small signals, okay? We have removed the DC component, which is, however, fundamentally important in order to give the DC energy to the memristor in order to amplify signals, so to be biased, as we said, in the NDR, and so to have the capability to amplify signals. But if it is poised in the PDR regions, here and here, the amplitude of the sine wave is always larger than the amplitude of the voltages across memristor and across resistor. So we are looking at 2 output ports. There are just 2 output ports here, one across the resistor, one across the memristor. But here it's interesting to see that you have, of course, amplification across the resistor, not across the memristor. Okay? So there is, across the resistor, the amplitude of the voltage sine wave is amplified. Then what we did is we increased the frequency, and we observed again that only when the memristor is in the NDR, you have amplification, again, only across the resistor, but now the amplitude has decreased before compared to earlier on. So this suggests some low-pass filtering behavior. Okay? So the amplitude, you see, it's not so large as before. And when we increase the frequency even more, at 10 megahertz, now there is no more amplification, not even across the resistor. Okay? So this means that there is a frequency limitation in the behavior of amplification. However, the NDR is fundamentally important to have amplification, at least in this system. Okay? What we did here is that we considered a simplified version of the model in order to make some analytical study. This is a model that we developed a few years back. It's based on the unfolding principle from Leon Chua. So it basically envisages the development in Taylor series of the polynomial series expansions for the state evolution function and for the memductance function, and then using an optimization algorithm to tune the parameters, to massage the parameters, in order to fit as good as needed experimental data. These are the parameters that we used, and we developed the small signal model, because what we did now is to understand better what was going on, because we were just having so far numerical observation. In order to understand better, we did assume a small signal stimulus, so we kept the stimulus amplitude very small, so that we could use the small signal model and the same approach that Professor Tesla showed this morning. Okay, so the idea is to develop basically the linearized model for the memristor to find its own small signal circuit theoretic model, which is basically a linear circuit where the elements depend on the operating point, because you make basically the Taylor series expansion of both state evolution function and Ohm's law, and then you transform the small signal model from the time domain to the frequency domain. Okay, so you can basically in circuit theory we can interpret this in a circuit model, and then we can derive the small signal impedance. And as you heard this morning, the small signal impedance is fundamental to check whether and when the memristor can become locally active. Okay, but for our interest, the local impedance is then embedded in the small signal model of the cell. Of course, we only consider the small signal stimulus, the DC component is removed, the resistor is linear, and then we have the small signal model of the memristor. And we can define two different transfer functions for the two output ports, a resistor-referred output function and a memristor-referred output function using simple voltage divider rules. As you can see, the transfer function depends only on resistance and on the local impedance. And so one can draw conclusion on the small signal voltage that will appear across the resistor or across the memristor depending on the small signal stimulus, basically using simple linear circuit analysis. So here again, the transfer function, and now we can plot the amplitude and phase response for the transfer functions at the three operating points that we analyzed earlier on. As observed, now we are actually considering the frequency we are sweeping the frequency, while earlier in the simulation we were only checking the behavior at a discrete number of frequencies. Again, the only interesting plot is the one that refers to the memristor being in NDR, because as you can see, the magenta curve for the memristor amplitude, for the resistor referred amplitude response is larger than 1 until a certain frequency. On the other hand, for the memristor-based local transfer function, there is no frequency at which the magenta curve goes beyond 1. Okay, so this is in line with the predictions that we earlier observed at discrete frequencies. let us see. So you have, interestingly, a low-pass filtering action here and a high-pass filtering action here, but it's this part is not interesting because, oops, something has happened. This part is not interesting because the memristive port is not amplifying, right? We have amplification only on the resistive port. One very important point to observe, but we can see this again here because we reproduce this here. This is very important. Here we show also, as you can see, the phase of the local impedance. Because if you remember from this morning presentation from Professor Teslav, the real part of the local impedance, the sign of it, when it is negative, the memristor is locally active. So it can act as a source of local energy. Okay, so we need to check. Real part negative means that the phase is larger than pi over 2. Okay, so until the phase is read here, until the phase of the local impedance is larger than pi over 2, the memristor, so in all this frequency band, the memristor is acting as a local source of energy. Okay, so this energy can be used for amplification. In fact, you can only have amplification when the memristor is sourcing local energy. So this is nice. However, we have a very interesting observation now. There is amplification only until a frequency here of 1.5 megahertz, of course, for the operating point that we considered, because this is all operating point dependent. But the memristor can actually act as a local source of energy for a larger frequency range. So this means basically that it is necessary for the memristor to act as a local source of energy and so to be biased in the NDR to have amplification, but it's not sufficient. So, because basically here, you see, in this frequency band, is not so tiny, it's from 1.5 to 2.4, the memristor is still sourcing local energy, but there is no amplification across any port. So this is an interesting observation. And here we have done an analysis with the Nyquist diagram, okay? So basically we have plotted in the complex plane the Nyquist diagram of the local impedance of the memristor. And for the discrete frequencies that we observed earlier in the simulation, we have basically created the link between the response across the resistor only, because we have amplification only across the resistor, and the Nyquist diagram evolution. So here we are at, you remember, at 100 Hertz, we have amplification, and we are at this point. This is the evolution of the with the frequency, positive frequency, okay, with the Nyquist diagram. Here we have we are at 1 megahertz. If you remember, there was still local gain, but it was decreasing. And here we don't have any more gain. Here is when the modulus becomes 1 for the local transfer function across the resistor. And this is, however, a range of frequencies where the memristor is still sourcing energy. Okay, you see that the real part is still negative, but there is no amplification. Okay. And here, this was the last frequency that we observed in the simulation. It was 10 megahertz. Of course, here there is no sourcing of energy and there is no amplification. So this is expected. So then what we did is, again, to understand something more, we fixed the frequency at 100 hertz, which was the frequency where the gain was quite large across the resistor. The resistor, we fixed it also. And we looked at the local transfer function for the resistor and for the memristor by changing BS. Of course, sweeping BS poises the memristor also outside the NDR. The NDR is the red one. Okay, so for 100 Hz, we observed that as long as the memristor is in the NDR, you have amplification on the resistor. But earlier, for the BS choice, we had this point here, so it was quite large. It is not necessarily large. It depends on where you are poising the memristor in the NDR. And you have no amplification, never amplification on the memristor, across the memristor, as you can see here, as in our BS choice. Then we increase the frequency. When you increase the frequency, it's interesting to observe that, okay, you see, earlier we were at this point. Sorry for these issues. Earlier we were at this point, okay, but had we chosen a VS smaller, okay, even if the memristor was in the NDR, there would be no amplification. So this is very interesting because you can have, I mean, as you increase VS and you enter the NDR, first you have no amplification on resistor, okay, here in this side. Then you start to have amplification on the resistor, okay, and then you have until the end of the NDR, okay. Across the memristor, you don't have ever amplification for this frequency. Okay, so at 10 megahertz, okay, here, irrespective of the choice of VS, you have never amplification, neither on the memristor, not on the resistor. Okay, so what is interesting, however, is to show here the operating regime of the memristor. Okay, so this is the critical frequency, as you can see here, when the memristor stops to act as a local source of energy. So when the real part becomes equal to 0, or if you want, the phase of the local impedance becomes equal to pi over 2. It's this dashed blue curve. Below this curve, so the area below the curve, so the blue area, this one and this one, they are the same, okay, is basically the regime where the memristor is on the edge of chaos, because we have stabilized it, if you remember, by inserting a resistor, a suitable resistor between voltage source and memristor, so it is stabilized on the operating point, and moreover, the real part is negative, okay, because below this dashed blue curve, the real part is negative, so the memristor is on the edge of chaos, okay. However, then we need to consider this violet curve and the violet area. So the violet curve is the critical frequency at which the local response, the amplitude local response across the resistor is 1. And below this curve, the area, the violet area, is the area in the frequency versus Vs plane for resistor equal to 100 ohm, where the memristor, the resistor referred local response in amplitude is larger than 1. So basically, this is the so-called sharp edge of chaos domain, because it's the subdomain of the edge of chaos region where the memristor effectively shows, induces complex phenomenon, in this case amplification in the circuit. The case study 2, we can go a bit faster. We only change the resistor, okay, to show that actually you can have amplification on both ports simultaneously. So in the first case study, we had only amplification across the resistor, but now by changing simply a resistor from 100 ohm to 25 ohm and repeating the analysis, okay, choosing, of course, DC voltages in order to drive the device in 3 different operating points for this value of the resistance, and keeping the same value Vm equal to 0.98, okay, we basically observe different phenomenon in terms of AC response. Without going into the details here, because now you have understood the procedure. So for 100 Hz, again, the PDO regions are very trivial, are uninteresting. You cannot ever amplify signal if the memristor is biased in the positive differential resistance. But in the NDR now, if you look at 100 Hz, both the amplitudes of the sine wave across the response of the circuit across resistor and memristor are in amplitude larger than the input amplitude. So you have amplification across both ports. Okay, and if you now increase the frequency, at some point, actually, you don't have amplification anymore on the resistor, but now it's the other ports that is amplifying. The only amplifying port is the memristive one for this higher frequency. And if you increase the frequency even further, even across the memristor, there is no amplification. So again, very interesting observations, but we have not yet come up with a conclusion on how to explain because there is so many parameters here, right? So how should I bias the memristor in which point in order to observe amplification? And amplification, for example, across both ports. In order to understand this phenomenon, we have used the Nyquist approach. Okay, so here again, we plotted the amplitude and frequency, amplitude and phase response of the local transfer functions across resistor and memristor. Once again, the all important one is the one in the NDR. Here it's interesting to observe that, as I said, at the beginning, you have amplification on both ports. You see, about 7 here and about 6 here. But then there is the first port that does not amplify anymore is the resistive one at 738 kilohertz, while the memristive one amplifies until 1.5. Once again, the memristor still operates as a local source of energy even after the second port does not amplify anymore. Again, NDR is necessary, but it's not sufficient for amplification. Okay. So this is actually a repetition, but just to look at in more close-up view. So you have amplification until 733 kilohertz across the resistor. Across the memristor, you have amplification even for larger bandwidth. And however, there is a range of frequencies between 1.5 and 2.4 where the memristor is sourcing energy, but it's not enough to induce local amplification across either port. So here again is the same concept looking at the Nyquist diagram and at the response. So we have at the beginning in this range you have amplification across both ports. From this frequency on, you have amplification only across the memristor. At this point, you have no more amplification across neither of the two ports, but in this frequency range, the memristor is still acting as a local source of energy because the real part is negative. The phase is larger than pi over 2. However, from this point on, of course, you don't expect any more amplification because now the memristor has stopped to act as a local source of energy. Again, we repeated the analysis as earlier on. We fixed a frequency and the resistance and swept the voltage Vs. And we have found a very interesting phenomena where basically, you see in the NDR, essentially, in the red region, you can have Vs values where there is no amplification across the resistor, even if the frequency is very low. Okay? So earlier we were here because we chose luckily, I would say, the value of Vs, because at this point we were doing only exploration, so we didn't know really how to choose the parameters, okay? But here the gain was very good, and similarly here, right? However, you see that there is it is not always the case that you have amplification in the NDR region, even at these flow frequencies. So it's very bias point dependent, this phenomenon, okay? Then when you increase the frequency, again, you have a similar phenomenon. You see, earlier on you had no more amplification on the resistor and still amplification on the memristor, but had we chosen a Vs a bit larger, we would have still amplification also on the resistor at this frequency. Okay, so here the choice was not optimal, for example. And then if you increase more frequency, so we can go a bit faster here. If you increase more the frequency, you see here no Vs value gives amplification, and similarly here for the memristive port. Now we wanted to understand better the phenomenon. Before going to this important step, I just show that we also, in this case, consider the edge of chaos domain and the sharp edge of chaos domain. In this case, you see that you have a violet area also for the memristive port because you can have amplification also across the memristor, right? So, of course, this is the domain, the blue area of edge of chaos, okay, where the memristor is acting as a source of local energy. The phase of the local impedance is larger than pi over 2, but you can actually exploit this energy only in the violet region, okay, which we call sharp edge of chaos, because only in this sharp edge of chaos region, you have both memristor acting as a local source of energy, and you also have the amplitude response across the resistor or across the memristor is in modulus larger than 1. In order to understand better, okay, here it's also another interesting plot where we swept, in this case we have Vm here and Vs here, you see? And we actually, earlier we only considered, you remember, two resistors, 100 and, so we did this case, and the other one was 25. If you remember, at 100, if you sweep the Vm in the NDR, this is only in NDR, because now we can just focus on the NDR, there is no way that you find frequencies below which the membristive local response is larger than 1. You see, you don't have the blue curve here, right? As we observed earlier, right? You have no amplification across the membristive port if R is 100 ohm, irrespective of the NDR branch, in fact. But if you are at 25, okay, here 25, we don't have it. You have 30, which is quite small, quite similar. You see that you have also a region where for R equal to 30, you can amplify, okay, across the membristive port. It's all the region below the blue dashed curve. While the red one, below the red one, is all the region where you have amplification across the resistive port. So you see you have some intersection where you have amplification across both of them, okay? Some frequency range but it's very nonlinear phenomena, okay? And if you change the model of your device, if you have another device, you will have other curves. So it's very device dependent, not only operating point dependent, of course, because the operating point depends on the device. So now, what I wanted to discuss is the conditions. Now, to understand better the condition for the cells to amplify. So we did some analytical study. Now it's completely, maybe because I was out of time. Okay, I try again. So basically, we want, of course, that the modulus of h of r is larger than 1. So if you do the maths, you arrive at this condition, okay? So this is the equation of a circle. And of course, if you look at the complex plane, this is the region where you have no amplification across the resistor, the attenuation region, we call it. And this is the amplification region, right? So it's enough that when we plot the locus of the Nyquist diagram for the local impedance, it enters inside this amplification region in order to have the frequency range across which, for a given operating point, for a given choice of resistor, here you have a normalized complex plane, we have amplification. So you can actually understand which frequency range is needed for amplification. So you need your local impedance to enter this region, this circle in red. We did the same analysis. So you see, you have amplification across the resistor when the Nyquist diagram, okay, in the complex plane, falls inside the circle of unitary radius centered at -1, 0. Similarly, we did analysis across the resistor, and in this case, you just need to enter a half plane, okay? As shown here, the half plane is described by this inequality. And now we can actually repeat understand this better, because we have the region of amplification and we have the Nyquist diagram. This is the first case study. Okay, so this is the amplification region across the resistor, okay? And this is the amplification region across the memristor. And this was the Nyquist diagram. You see that the Nyquist diagram earlier was never entering this region. That's why we never saw amplification across the memristive port. No frequency could allow this. But we entered for a certain frequency range inside the circle for amplification across the resistor. So this explains beautifully, using this control theoretic technique, the amplification properties of the cell. And this is the second case study. Okay, the Nyquist diagram was the same because we biased the device in the NDR in the same operating point, if you remember. It was just our choice. But now, interestingly, we also enter the amplification region for the memristor. And actually, we can amplify across both of them for the frequency range. So this explains beautifully with this very standard tool that we all explain to our students, the properties of amplification for this cell. So I think that we have some other analyses where actually we have derived the analytical formulae for the critical frequencies, but I think we can skip these mathematical details. We have some frequency at which the critical frequency for the resistive port amplification. We have the critical frequency for the memristive port amplification. We have the critical frequency for the memristor to act as a local source of energy. So all is explained using local activity theory. So in conclusion, and now we are actually working on multi-stage amplifiers. Of course, there are some limitations in this approach. So we don't believe that this will rival or compete with the CMOS, but it's an interesting theoretical development anyhow. And we have found very, very intricate behaviors when we couple multiple cells one after the other. From a nonlinear dynamics perspective, it's really beautiful. I don't have time now to show this, but honestly speaking, regarding also looking at the experimental tests that we are looking at NumLab, we need a lot of work to improve these cells, and I don't believe this will rival CMOS ever, honestly. But it's interesting to explore, for research. Anyway, we have a lot of interesting also application of threshold switch beyond the signal amplification. Okay, although there is a hype now because Stanley Williams have this Nature paper where has shown that you can boost signals across the transmission line using edge of chaos media. Okay, so maybe our device is not perfectly suited for this amplification purpose, but other media can be explored in the future. So basically, you can have different type of application, and here we listed some of them. Signal amplification. You can reproduce neuronal bifurcation, so you can create more bioplausible neuristor and neuromorphic circuits and systems. You can design robust oscillators. We haven't touched this point, but we have done a lot of work. You can explain fundamental open questions in science, such as Small paradox, Turing instability. We have touched them without going into the details. You can develop also very interesting, innovative, compact, and energy-efficient topologies for bistable cellular nonlinear networks. And we have here work of Ahmet Demirkol. If you're interested, we can share with you. And you can also solve complex optimization problems, such as the graph coloring, as Professor Tesav explained in this morning. So one thing important for us is that the dynamical system theory is very important to explore the full potential of threshold switches in electronics, either be positive result or a negative result, but our nonlinear dynamic approach can actually shed light into the limitations or into the potential of these circuits with memristors on at the edge of chaos. Thank you.
So you can operate at the edge of this region and in the middle of the region. Is there a difference?
That's a good question, very good question. Yes, I mean, of course there is a difference. For example, when we derived this circuit that was reproducing a Turing instability phenomenon, okay, we were biasing the device in the edge of chaos, but on the very closely to the bifurcation locus, okay? And so this means that you need just a tiny perturbation to induce the excitability of the cell before the bifurcation. So of course there are in fact, when you look at the bifurcation diagram of the Ocean and Huxley, it is still on the edge of chaos, so as shown in this beautiful paper from Leon Chua. It is still on the edge of chaos when it experiences the bifurcation, but the region is a bit begins earlier. So typically, when you have when you are at the edge of chaos, typically, okay, you have some local bifurcation there.
Okay, the next question was about the amplification itself. So, can you predict the level of amplification? Will the signal be twice as big? And what is the bands on?
Yes, this can be easily inferred from the local transfer functions, because you have a simple voltage divider. At least when you have a frequency, when you're at zero frequency, okay, the small signal impedance corresponds to the small signal resistance, right? Which is negative because you are in the NDR. So you have a simple math, R divided by R plus small r. And the small r, depends on your device, how it is, the small signal resistance at the operating point. You do the math, this is the gain you can get. And of course, you can play with the denominator to increase the gain. Okay. The problem is the technological problem. For example, in the devices that we have at NumLab, at the moment, they don't work very reliably. When you poise them in the NDR, they're very unstable. There is some unstable phenomenon going on. So now, for example, they are developing a new series of devices, make them more carefully in order to make them more robust, and then we can explore better also experimentally. That's why I have some experimental results, but I didn't show them because I think that we can do much better. We have done, however, a demonstration, which is interesting. We show that we were able to measure the local impedance, okay, and to demonstrate that the local impedance was for the whole for the resistor memristor one port series one port, okay, and we have shown that the behavior across by sweeping one of the bias parameters, so that we could enter both PDR and NDR. We showed that basically the behavior of the local impedance in the NDR was a demonstration of the amplification property. However, in the looking at the waveforms of the signals, they were not so beautiful as in the simulations because of some very weird phenomenon going on in the device. So we have still to work on the experimental side.
Any other questions? No questions? Then then I asked about the frequency. So I'm working on the radio frequency range, but these memristors still working in a kilohertz. I think up
Yeah.
to 10, something.
Yeah, as we saw, the available frequency band for the amplification was up to the frequency about, for the operating point, we considered it was about 2.5 megahertz, up to the frequency where the memristor was acting as a local source, was still showing a negative real part in terms of local impedance. So basically, but the amplification stops earlier. So about what depends on the operating point, but typically yes, a few megahertz for this amplification. Megahertz. Yeah. For this amplification.
Still, yeah.
But the problem is that these devices have also parasitics. Okay, so if you increase too much the frequency, you might excite parasitic effects, so you see something else. Okay, so instead of just the local impedance of the memristor, you see the local impedance of the memristor with in parallel a capacitance. So things can change, and of course, if you add the capacitance, you have a higher order system. You can see more complex nonlinear dynamical phenomena. So there are some technological issues in this device that have to be improved in order to act to operate as desired.
Still, it's interesting to see just the idea that it's possible to do that. Okay, so any other questions? If no, so I was asked to give you one present from the organizers. So thank you for your nice presentation. It was really interesting, especially for me.
Thank you.
So thank you very much, and this session is over. Thank you.
Need something? Thank you. Thank you very much.
This?
For you. Some water.
I ask the speakers to be mindful of time, and John will have 15 minutes, and then we will have a couple of minutes for discussion. So the first speaker is Professor L, and the topic of his presentation is common finding differences that computer functional derivative definition for one-dimensional space fractional diffusion equation.
Pointer?
I think that we should have a pointer
Here.
here. So this is moving forward, backward, and this is for pointing. So you point like that.
Okay.
Okay? Okay.
Okay, hi everyone. My name is Neslihan Fatma Er. I am from Istanbul Kültür University, from vocational school, Istanbul. Now, I want to present my study named as Compact Finite Differences Methods and Computer Fractional Derivative Definition for One-Dimensional Space Fractional Linear Diffusion Equation. And as a first part, I want to summarize my outline. I will start with introduction part, then after that mathematical formulation and compact finite differences schemes. After that, I will try to explain a numerical example for that method, and after that, the dispersion analysis of the problem can be handled. And finally, the conclusion will be with you. Okay, what is studied? The scope of my study is one-dimensional space fractional non-homogeneous diffusion equation with initial and boundary conditions. The problem which I handled is a kind of boundary condition with an initial conditions, and it is solved by the compact finite differences method. The fractional part of the equation is processed through the Kappa fractional derivative definition. In the solution, finite difference discretization is carried out, and along the time coordinate, not the spatial coordinate, space coordinate, and a fifth order compact finite differences scheme is used along the spatial coordinate, and the applied method is shown to be an applicable technique that approximates the exact solution very well. Here the keyword is Kappa fractional definition. Of course, the problem, which is space fractional linear diffusion equation, and compact finite differences schemes, and dispersion analysis. The motivation for high order accuracy is the important part of the study. So the taking numerical aspects into account, there is an ascending interest in methods that possesses a high order of accuracy. With standard finite differences, high order accuracy for ordinary differential equations and partial differential equations is obtained in two ways. In first way, the first way is increasing the number of nodes. Increasing the number of nodes makes the mesh sizes smaller, but enlarges the computing time and the required many storage space. On the other hand, the second way is using high order schemes, and this increases the stencil of grid points and the bandwidth of the stiffness matrix, which makes a fast direct solver difficult. While applying the method to the problem, the central idea was it is possible to obtain high-order accurate solutions using compact schemes, which handle the small complexities near the boundaries with different approximations. Finite differences schemes are classified implicit and explicit. As implicit and explicit. In explicit schemes, the area represented by the problem is expressed by the nodal derivatives as an explicit weighted sum of the nodal values of the function. In the implicit schemes, if you decide to use implicit schemes, these schemes equate a weighted sum of the nodal derivatives to a weighted sum of the function values. And for small scales with the same stencil width, implicit schemes are more accurate than explicit schemes. So we used implicit schemes in this study. So this accuracy gain comes at the cost of inverting the band matrix built from the coefficients of the unknown nodal derivatives. If we want to compare the implicit versus explicit matrices as a concept, in the aspect of derivative form, explicit schemes weighted sum of the nodal values, but implicit schemes weighted sum of the nodal derivatives, which is equal to weighted sum of the values. Accuracy stencil in the aspect of accuracy stencil, explicit schemes is lower, implicit schemes is higher, and in the aspect of computational cost, explicit schemes give direct evolution, but implicit ones requires band matrix inversion. Studied for compact schemes in explicit schemes is less, but in implicit schemes, small stencil and high order accuracy. Under this comparison, it is reliable to choose the implicit schemes. We use implicit bands matrices that are usually chosen as tridiagonal, since tridiagonal matrix can be inverted quite efficiently. Because the disadvantage, implicit methods are advised to be used together with compact schemes. Compact schemes supply high order accuracy with a small size stencil, so they are widely applied to computational problems. These are the reported applications used with compact schemes. Steady convention diffusion problems, the Poisson equations, the Helmholtz equations can be solved with compact schemes with a higher accuracy. Okay, mathematical formulation of the compact finite differences schemes. We have to grid, set the grid for the in the boundary conditions for the problem, and first derivative schemes. If we consider n nodes on a uniformly spaced mesh indexed by n on the interval of a and b, then the steps are calculated b minus a over n minus 1 and is abbreviated as h. And each nodal points is presented here, are presented here as xy. Our interval is between 1 and n is the number of nodes that we choose it. The finite difference approximation to a derivative is linear combination of the given function values. The first derivative, fi, depends on the neighboring nodes. And implicit compact approximation, the first derivative can be expressed by the first equation, as you can see here. The relations between A, B, C and alpha, beta coefficients can be calculated, but while we are solving the problem, we set beta and C to 0, and so we get fourth order three-diagonal schemes. For the second derivative and the boundary formulas, both sides of the equation 1 that I showed a moment ago are expanded in a Taylor series about about each point, which is represented as xy in each step, which is called as h, then grouped by order of h. Matching terms determine the unknown coefficients. Then we can calculate A, B, and D coefficients here. Inner points are also problems. With the calculated coefficients, the schemes for the inner points from I equals 3 to the point n minus 2 can be calculated like that. These compact stencils give fifth order accuracy and sixth order accuracy for the first and second derivative, respectively. And some more calculations should be done here for the second nodal point and the nodal point before the end. After some calculations, the final compact schemes are shown in the slide now. Equation they are obtained by the equation 3 and 4 are adapted for A equals n together. The equations from 5 to equation 10 cover all inner and boundary rules. Then, if we take 7 nodes, nodal points, the compact schemes give the matrices like that, and we can represent the matrix equations just like in the equation 11 for the system for the first derivative values. And after that, LU decomposition should be done. LU decomposition is applied to the known matrix A1. As you see here, I don't want to read all the equations here, but you see the calculations. At the end, the first derivative representation is obtained at the equation 17. And the similar calculations are done for the second derivative matrix system. You see the LU, the equation 18 is similar LU process, is obtained by the similar LU process, and the discretization is built by the substituting equation 17 and 19 for the first and second derivatives. And after that, for the partial derivative parts of the problem, we used Caputo fractional derivative definition. The fractional derivative part of the problem is solved by using this definition. The gamma function is used for the fractional order alpha, and the Caputo form requires the integer order derivative fn inside the integral, which fits naturally with the compact approximations of first derivative and second derivative of the function derived above. After the explanation of the method, let's look at the test problem. A one-dimensional fractional linear equation is given in the equation 21, and this problem is defined on the interval for x and time, and the boundary and initial positions you see here. And initial condition is given with the function x cube, diffusion coefficient, and source and sink equation. Exact solution is like that, and we applied the Caputo derivative first. Taking n equals 2, the fractional derivative terms becomes like that. Our derivative degree was 1.8. Then the nearest one, the integer number is 2. Then we had to take the n equals 2. Then we applied the Caputo derivative definition to this one, and it is reduced to the equation you can see at the below. After that, the problem should be discretized. After the discretization process, the final discretization scheme is obtained as shown in the equation 29, and with known boundary values entering through the matrices you see here at the bottom. So they are accounted in the constant C1 and C2. Result is the graph of the solution you see here for n equals 121 and the k 0.001, and for different k values, step values, you see the different results here. The solution surface reproduces the expected diffusion profile, and the method approximates the exact solution very well. And after that, the dispersion analysis is done for the completeness of the study. Numerical dispersion analysis shows that the method is convergent and consistent by comparing dispersion equations in continuous and discrete. For the continuous dispersion equation, the general single wave solution of a linear partial differential equations is inserted to the equation 24. The right-hand physical effect terms is set to 0 since the dispersion relation links the angular frequency omega to the wave number k. For the discrete dispersion equation, the discrete general solution is used like that in equation 31 and 32. If it is rearranged for the equation, and continuous dispersion equation is obtained by inserting the x derivatives, spatial derivatives of equation 30 into 24, and we let the alpha as e to the I k x plus omega t. The non-homogeneous term qxt is set to 0. Then the continuous dispersion equation is given in the equation 38. Then the final work is to compare the discrete and continuous dispersion relation. Discrete relation is obtained by these calculations. These are very long calculations, but the summary is here. And this is the compareness of continuous and discrete curves. The solid curve is the continuous one. The dotted straight curve is a discrete one. The two curves intersect at many points, and since an intersection at only one point is sufficient in this method, the scheme is consistent and the numerical results converge to exact solution as h goes to 0. As a conclusion, the method for our problem is a hybrid, actually, a hybrid for one-dimensional diffusion equation. Finite differences are used along the time dimension, compact schemes used along the space dimension with the accuracy order of 5 and 6 for the first and second derivatives. Errors are computed by comparing the solution for fractional order of 1.8 with the exact solution for the integer order of 2, since the exact solution for 1.8 was not available. This is defined by the Caputo derivative method. And dispersion analysis shows that the discrete and continuous dispersion curves intersect at many points. As I said before, one intersection is enough to complete convergence as h goes 0 consistency. So we can say that compact schemes together with the Caputo derivative definition are applicable for the fractional diffusion equations. I will skip this because I already mentioned about this while I am presenting. And these are my references. And thank you for kind attention. That's all.
Are there any burning questions? If not, let's take the speaker again. Move to the next speaker. I don't know if we have to share it. And announce it for me there. Sorry, I forgot your first name. And he will speak about bridges and genus and uncertainty classification for nominal pairs approaches to the largest value response.
Okay. Okay.
So try to be around.
Fit. Perfect. Okay. 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 Okay, thank you very much. I am Adrián Garcia, and I'm going to talk about how we can connect a stochastic system with chaotic system. So the main idea of this study is that, well, okay, we know chaotic systems are not stochastic systems. They are very different, but maybe we can use some tools designed for the study of stochastic systems into gain knowledge about chaotic systems. So, for example, the typical system that gives me the idea is turbulence flow, turbulence in general. There are several authors that try to model turbulent flows just as chaotic systems without using any noise or any stochastic or randomness. While there are other authors that model or try to study the effect on turbulence of some white Gaussian noise and try to study its effects. No? So this may lead us to connect or relate that there are some common aspects between a stochastic system and chaotic system, and maybe we can interconnect some tools to study them. So this is not a finished framework or a finished study. It's just some try or some initial work to try to connect this system. And the focus of this work is the largest Lyapunov exponent because it's somehow intuitive that the dispersion in trajectory may be related to the expansion of the growth of variance in the movement of the system, of the particles of the system. Okay, so related to that, first an initial definition. We all know that the largest Lyapunov exponent tries to quantify the exponential rate of separation of two very near trajectories. Okay, and we have the traditional equation that we use to compute it, and there are several algorithms to compute it. Some of the most well common is the Wolf method, but of course there's several methods. Some of them has some advantages, some of them has some disadvantages, and we can work with that. No? But in this case, we try to propose a new method to compute it using stochastics methods. Okay, and we relate that growth in the ensemble variance, in the variance of the system with the largest Lyapunov exponent. Okay, so part of the results of this study are published in the Chaos Journal in this paper. So maybe if you don't understand right now, you can check later on that paper and try to close the gap. Okay, so just to compare with our method, this is the typical Wolf algorithm. We start propagating the nonlinear system with two trajectories, one near the other, very, very close to the other, and we measure the separation between those two trajectories, and we compute with this equation the largest Lyapunov exponent. So nothing new from this point of view. Okay, but we can show that that exponent can also compute it if we propagate a probability distribution using those systems and measure how the variance grows with time. Okay. There are several methods that we can use to compute. No? The idea is instead of starting with a single trajectory, we start with an initial point and a probabilistic distribution around that point. And we measure the initial variance of that probability distribution from the initial time to some time after that. Okay? We can measure or we can propagate that variance with several methods. In this study, we try to use the polynomial chaos, but you can use Monte Carlo experiment, you can use several methods, okay? And it works with every one of those methods. The question is, maybe some of those methods can add some advantages to the calculation of that Lyapunov exponent, okay? So again, with polynomial chaos, it's not evident that we gain some advantages over traditional method. It's not maybe as computational cheaper as the traditional Wolf method, but this can open to new research lines that maybe have some advantages in the future. Okay, this can use what we call intrusive methods, in which we have to know the equation of the nonlinear system and we have to work with those equations, and this can apply to non-intrusive version of the polynomial chaos method, in which we don't have to modify the initial equation, so they are cheaper and easier to implement. And this plot or this figure shows the main idea. We have an initial point and we have a statistical distribution that models the uncertainty in the initial position of our system. Okay, and if we propagate that enough time, we arrive to a similar behavior of the chaotic system, in which the deformation of the initial Gaussian distribution aligns with the large Lyapunov exponent direction. Okay, so we can start with a Gaussian distribution, or we can start with any stochastic distribution, any probability distribution, but with enough time, we see this behavior. And we can compute that Lyapunov exponent, measuring the growth in the variance. Okay, this sigma is the covariance matrix, so the variance is the trace of that matrix, and we can see how the aspect ratio of this, in this case, to the distribution, grows with the time. Okay, following this, the difference between the largest and the second one, Lyapunov exponent. Okay, so now this is the mathematical framework on how to implement the polynomial chaos in the non-intrusive version and in the intrusive version. Okay, so just to summarize, in the non-intrusive version, we have a differential nonlinear operator that, as it is a stochastic system, we have some stochastic variables, and the solution depends on that stochastic variables. Okay, so in the non-intrusive version, we project the solution into a space of functions that are orthogonal by the vectorial product defined by the probability density function. Okay, so this probability density function depends on the stochastic variables that we are using in our problem, and with that we can define a vectorial product, inner product, sorry, and this defines a set of orthogonal functions that we can use to project our solution. Okay, so evaluating the evolution of discrete points into time, we can then recover the evolution of that coefficient following a quadrature rule, and then we can compute the mean and the variance that are propagated into the field. With that variance, we can compute the Lyapunov exponent using our definition. Okay, and in the intrusive version, it's more complex because we have to use the inner product defined in the previous slide to project the original equation, the original operator, using each function of the basis. Okay, so at the end we have a nonlinear system of equations that we have to integrate with a standard time integrator. Okay, so in any case, the algorithm is relatively easy to understand. We initialize our system at a point and with an initial uncertainty in the initial position of the initial state of the system. We propagate in time, and we are going to measure the growth in the variance at certain time interval. Sorry. As in the Wolf algorithm, we need to renormalize the uncertainty distribution, the probability density function, because, well, it's in the same case that in the Wolf algorithm, that at a certain time, the uncertainty is so big that it doesn't follow the Lyapunov direction. Okay, but after that, we can compute using the temporal mean, the largest Lyapunov exponent. Okay, so of course, non-intrusive and intrusive methods, each one have advantages and disadvantages. But in any case, we can use both of them. Okay, so to show you some results, in this case, we can, or in these figures, we have validated the uncertainty quantification technique. That means that we, using polynomial chaos, are able to propagate the variance following the true variance, okay? And we compare it against a Monte Carlo experiment. And here maybe are the most interesting figures that show for the Lorentz system, the standard Lorentz system, some realizations of the Wolf algorithms and our own algorithm based on polynomial chaos. Okay, what is important from our point of view is that both methods converge to the true value of the Lyapunov exponent. Okay, and the rate of convergence is more or less similar one or the other. Okay, so this is also validated against the Rosler chaos system, and is also validated using non-intrusive version of the algorithm. Okay. Of course, we don't want you to believe that this polynomial chaos is, from the numerical point of view, faster than the conventional Wolf algorithm. This is not the discussion, I think. The question is that we can, from now on, try to achieve new methods to study the chaotic system. Okay. Nevertheless, for example, in the non-intrusive version of the method, there are, or they depend on several parameters. They depend on the results, the accuracy of the method depends on the initial variance of the distribution, on the number of intervals we choose to apply the method, the normalization time, several questions, okay? That requires maybe more time to fully understand or to fully characterize the method. Okay, I think this is the time. Thank you very much. Sorry?
8-6.
Okay, yeah, sorry. Yeah, you take a point and then a probabilistic distribution around that point that models the uncertainty in the initial condition. So it's like you don't know if you are here or here or here or here. You are this one. Okay, if you take this probabilistic distribution and you propagate in time, after some time, you have this probabilistic distribution. So this more or less is in all directions the same probability you find the point, but after some time, this is the form, so it's most probable to find the point in this direction. That is the direction of the largest Lyapunov exponent.
Which puts up probability.
Yeah.
Can I ask something? So here, what are you integrating? You're integrating your initial point and the nearby points, or what?
That depends on the uncertainty quantification method you are gonna use. Okay. So, for example, if it is the Monte Carlo experiment, yes, you propagate that point and you propagate 1,000 points, and with that it's done. Okay. In polynomial chaos, if it is the non-intrusive version, instead of propagating 1,000 points, you propagate just 20. Just 20 points, for example. 10 points. 10 points that are at some certain position around the point. In the intrusive version of the method, you have to integrate a modified nonlinear equation of the Lorentz system, for example. Okay, and with that, it's like you propagate the coefficients of the stochastic function basis that you are using.
But in the usual version, you have one point and one real. So then you have 2 points. 2 points.
Yeah.
In the Wolf algorithm,
Yeah.
your fixed and the perturbation, so you have 2 points.
Yeah.
So here, or in all the other portions, you have quite a few more points.
Yeah.
So computationally, how do you gain?
Yeah. No. Of course, you don't gain from the point of computational. You don't gain from this perspective. You don't gain anything.
Because you also said that they converge more or less at the same time.
Yeah.
So that means that you have spent more.
Yeah.
Significantly more computational.
Yeah, but what I expect into the future is that this may be related not only to the largest Lyapunov exponent, that it may be related to the full Lyapunov exponent. Spectrum, yeah, sorry. And in that case, maybe this can lead to numerical advantage. Because this also depends very much on the uncertainty quantification you choose. So in this case, we don't gain any numerical advantages, but you can try this technique with another 20 different algorithms, and maybe in some of them you can gain something.
So we'll do that. Thank you so much.
Okay.
Any other questions? If not, thank you so much. So it's your turn, Dr. Lasagna.
Yes.
And this resolution will be practical variation of optimization for various solutions of determinants.
Yes. Okay. When it starts. Okay. So I'm going to tell you about some work that me and my postdoc Tom have done over the last few years. So Tom is now my postdoc, but he used to be my PhD student. So this is kind of his PhD work. And I was the lucky one to be able to come to Greece from the grey UK, actually, to this nice sun. Okay, so I'm going to talk about methods to find invariant solutions in fluid turbulence. So my background is fluid mechanics. So I come from an aeronautics and astronautics department. So I'm going to try to make this talk accessible to people that don't know much about fluids. Okay, so in the last 20 years or so in my community, people have started to use dynamical system theory more and more to understand fluid turbulence or turbulence in fluids. Yeah, and one of the things that people have done a lot is to search numerically for invariant solutions. Equilibria, periodic orbits, but for systems that have continuous symmetries, then these are relative objects. So they are equilibrium moving frame of reference, for example. So what you see here is two examples of traveling waves in pipe flow, round circular pipe. Yeah, so if you were to look at an animation of that one, you would see some sort of fluid motion that travels to the right. And people have done this because fundamentally you can find these simple solutions and they tell you something about the structure of turbulence. Yeah, so by analyzing simpler objects, we can understand more about complex fluid flows. But also the other thing that these invariant solutions are quite helpful for is to form some sort of map of state space. So in fluids, state space is thousands, hundreds of thousands, millions of variables. Yeah, so we need some tool, some low-dimensional projections to understand the structure of state space. And invariant solutions can help to do that. So what you see there is a sketch, a 2D sketch of potentially large-dimensional system. This is actually the phase space of pipe flow. So what you have, if this works, yes, this one. Yeah, so this is the laminar flow. It's stable, so it's an attractor. So it's got a basin of attraction, potentially fractal, who knows? And this basin has a boundary that is riddled in practice with invariant solutions, traveling waves in particular. So by finding numerically these invariant solutions, we can find, or we can understand better the process of transition from laminar flow to turbulence, which is important in many applications. But also beyond transition, if you're interested in understanding turbulent dynamics, what you can do is you can potentially find periodic orbits and understand a bit better what the structure of the attractor is. Yeah, so there's a dynamical perspective to turbulence that has been kind of more prominent in recent years. There's one big problem in my field, which is that we've got one parameter, which is the viscosity of the fluid. So actually the non-dimensional number is the Reynolds number. So when the Reynolds number goes up or viscosity drops, then finding these solutions is more and more difficult because the state space dimension grows. Yeah, you've got higher and higher dimensional systems, plus the trajectories there are more and more unstable. Yeah, so numerically, this becomes quite a challenge. So there's two families of methods that people have developed to find invariant solutions, and I'm going to focus on periodic orbits. The first one that you may be familiar with is the shooting method, very classical. So these are the Navier-Stokes equations. This is the momentum equation, the governing equations for fluid flows, the PD, so that N has advection and diffusion, and then you've got pressure, the pressure gradient there, which is kind of nasty because mathematically helps enforcing that incompressibility constraint. We want divergence-free velocity fields for incompressible flow. So if you've got some sort of time stepper, a numerical solver for this PDE, what you can do is you can simply march an initial state, U0, to its final state, UT, through this numerical time stepper. And then the shooting method effectively tries to find a state, U0, that occurs exactly to itself after some time t. And to do that, you have to solve this nonlinear equation. It's just a root finding problem. You have to find U0 and t such that that is true, with G being your numerical integrator. This is nice because you can use Newton-Raphson method, which is quadratic convergence. So once it kicks, it starts going down very quickly. But the basin of attraction of the Newton method is very small. So you have to be very, very close to the roots for the method to converge. So there's techniques to actually improve robustness, but shooting methods in practice has been quite flimsy or weak as viscosity drops. Plus, there's a bunch of other machinery that you need to introduce to make the method viable. So what we've been doing with Tom is come up or develop a different strategy, where now the idea is that you start from a closed loop in state space, so it satisfies periodicity, yeah? And potentially also the constraints of the problem, the incompressibility and the boundary conditions. But this is not initially a solution of the equations. It's got a residual. Yeah, there's a mismatch between the vector fields and the loop tangent. And this equation has a residual because it's just a guess. So what you need to do is you need to adjust this loop in state space until it becomes a solution of the equations fundamentally. And that's a different strategy. Earlier, we solved the equations exactly, but we didn't have periodicity. Here we have periodicity, but we're not solving the equations yet. So the strategy that we have introduced is to try to find the loop by solving an optimization problem. So the idea is to find U, the loop, in state space and the period t that minimizes this mean square violation of the equations. Yeah? So if the residual, small r, goes to 0, then you found a solution of the equation. So the minima of this objective function here, this function at r, are periodic orbits. So this is nice-ish because this is still a constrained optimization problem. You have to find a minimum of that subject to the incompressibility and the boundary conditions. Yeah? So that's a constrained optimization problem. But it's nice because we have an exact gradient. Yeah? You do variational calculus on this PDE. It's not as straightforward to do. So you've got an exact gradient expression that you can use, which is nice because you can do gradient-based optimization, which is what we do, which is supposedly more robust than Newton method when you start away from the root. But unfortunately, this is a constrained optimization problem, so it's slightly harder to tackle. Plus, we don't know much yet. Well, we kind of do, but at the point of studying this, we didn't know much about the conditioning of the problem, how easy it is to converge to a minimum. So the strategy that we have to get rid of those constraints is very straightforward. You just rewrite the problem variables. Yeah? You introduce a transformation of the problem variables so that the problem becomes unconstrained. So this is done through what's called a Galerkin expansion, which is a nasty name, but the concept is very easy. The idea is that you represent your velocity as a weighted sum of basis functions that satisfy the constraints already, and you weight those basis functions with unknown amplitude coefficients, which now become the optimization variables. Yeah, so for any choice of A, the coefficients, the velocity satisfies the constraints, and then you solve the optimization problem for the variables A, the coefficients, rather than from the with the velocity field. Yeah, so this is a trick to transform the problem into an unconstrained problem, which is easier to solve. Doesn't matter very much for you, but we find these MAUs, these basis functions psi, using a technique called resolvent analysis, which is very popular in fluid mechanics at the moment. Nevertheless, so the algorithm that we have is basically, effectively, based on these two steps. There's an expansion step where you go from coefficients to velocities, and there's a projection step where you go from velocities to coefficients. Yeah, this is, imagine just a matrix that transfers U to A or A to U. It's a change of variable fundamentally. So the flow of computation is as follows. For any A, you want the objective function and the gradient. So what you do is you first expand. Yeah, you get the full velocity field. You compute this partial residual, which doesn't have pressure yet. So this is not the actual residual that we need for the gradient computation. This is easy to do. This is just evaluation of advection and diffusion. So it's very straightforward, very cheap to do. But to go to the actual residual that we need, R, yeah, we do this projection expansion step. So this projection expansion step effectively projects this R tilde down to the space of residual fields that satisfy the constraints. Yeah, there was another trick that we need to do. And once you've got the actual residual, then you evaluate the global residual, the objective function, and the gradient, which you project again in the coefficients. Yeah, so you go from coefficients to everything you need for optimization. So to do this, we have a Julia package. Anyone uses Julia in this room? Julia programming language? Not so much, okay? So we use Julia because it's kind of a nice language to do all these computations in. We develop a package to generalize the nasty bits of this algorithm, so spatial discretization, so FFTs, and then finite differences, the expansion and the projection, and then we have several optimization algorithms that we can use. We use mostly LBFGS because that's the best we've found so far. The thing is that this package also allows us to do space-time decomposition. Didn't say this earlier on, I have to go back. Yeah, but anything that you see as U of R is effectively space-time trajectory. So it's a 4-dimensional array effectively when you store it on the computer. Yeah, because you have to store 3 Cartesian coordinates and time. So it's a huge memory-wise object. Yeah, so we can use memory, we can use space-time domain decomposition techniques. That's what we do using MPI, the message passing interface, to distribute computations on multiple nodes. And we are working towards putting this on a GPU as well. Okay, I'm going to show you an example of this gradient-based optimization. This is from Tom's PhD. And we're going to talk about Taylor-Quet flow. So Taylor-Quet flow is one of the canonical flows, canonical setups in fluid mechanics. Is the flow between 2 counter-rotating cylinders, yeah, with different radii. And we study the narrow gap limits, yeah, when the 2 cylinders are equal in diameter. So you effectively have a very narrow gap, which gets rid of curvature. Yeah, that's why we study the flow in a rectangular Cartesian domain, but rotation is still there. Yeah? So there's a centrifugal instability that kicks in a simpler geometry. So these are the equations that we solved. This is Navier-Stokes equations, advection, pressure gradients, diffusion, and Coriolis force for the rotation. It doesn't matter very much, but we consider a special case of that, where the flow does not depend on x. Yeah, the flow is azimuthally independent, because that's what kicks in after the first bifurcation in Taylor-Quet flow. Yeah, so it's kind of easier to deal with, and I'm going to show you results on that rectangular domain where we've got those 2 rods. So this is a numerically sampled homemade bifurcation diagram. There's no continuation here. It's just purely running numerical simulations using a time stepper as a function of the Reynolds number. So we are decreasing viscosity as we proceed to the right. So the bifurcation variable here, it's K, it's some sort of global variable, some kinetic energy of the velocity field, fundamentally. The critical Reynolds number, the supercritical bifurcation, occurs at 20, and you see there several branches. This is numerically generated, so it's the state you end up in depends on the initial condition that we use for the simulation. But these branches correspond to steady roll-like structures. These are equilibria, yeah? And you see several branches because you can get multiple states with different number of rolls in that domain of length A. If you push the Reynolds number a bit further, you drop the viscosity, there's going to be a Hopf bifurcation up there, and the system transition, the state transition to a stable periodic state, where you get unsteady, wavy rolls. Okay, so we're going to study, well, if you push Reynolds number further, you end up in chaotic regimes, which we did not touch very much. So we're going to study the performance of that optimization-based algorithm on these 2 cases here. So top row, initial condition for the optimization, random or kind of ad hoc. That's the final result after the iterations have converged, and this is the result from the numerical simulations, of course, that you coincide, and this is only possible because it's a stable object, so the simulations converge to it. But these 2 are actually identical. These are the simulation the optimization traces. That's the objective function that we're minimizing. Yeah, lots of iterations. The residual drops very, very quickly initially. That's good, but then it plateaus a little bit, stagnates a little bit. Yeah, so that's not very nice. So we did some analysis to try to understand why that's the case. And I'm going to give you a very brief summary of why this slows down like that. So near a minimum, let's say that U star is the minimum. Yeah, so the function and its gradient are 0. Yeah. Then the behavior of the functional R, the objective function, is determined by the properties of the Hessian. In finite dimension, this will be a matrix, yeah? And that controls whether your paraboloid near the minimum is, well, it controls the shape of that paraboloid fundamentally. So if you eigendecompose that Hessian, you can calculate a condition number, the ratio of the largest to the smallest singular value, eigenvalue. So if the condition number is 1, you've got a round paraboloid. Yeah, so the optimization problem is very easy to solve. Gradient descent would go down to the minimum in just one iteration. But it turns out that the condition number is not that bad. It's not that nice, actually. And that's why, fundamentally, you observe that poor convergence rate in the optimization. So two things affect the condition number. One is the linear stability of the solution near the minimum. Yeah, so effectively, if the linearized operator, the linearization of the right-hand side of the system is close to being marginal, then the condition number goes to infinity. And we found that experimentally, numerically, by doing optimizations as we approach the critical Reynolds number for bifurcation from above. As we drop the Reynolds number, the iterations slow down because we're getting closer to the bifurcation. Yeah? So this means that fundamentally, it's going to be increasingly difficult to find near neutral solutions. The second thing that controls the convergence, and that's my last slide, is how many modes we retain in the expansion. Yeah? It's the dimensionality of the optimization vector A, fundamentally. So it works out that if you truncate that model basis from 8 to 64, you get a dramatic effect on the convergence speed of the algorithm. Yeah? And typically, the more modes you have, the slower the iteration becomes, fundamentally. This is in a log-log scale, so you see there's 2 orders of magnitude difference. But that's good in the sense that even if you add more and more modes, at some point, the accuracy of the method sort of stops or plateaus. What you see on the y-axis is the L2 norm of the difference between the truncated solution and the final solution, the full state solution. Yeah, so after 10, 15 modes, you don't gain much by adding few modes. You just make the optimization much slower. Okay, conclusions. 3 things to remember out of this. So we use gradient-based methods to find periodic orbits and not the Newton method. This has, hopefully, larger Bayesian attraction for those solutions. We use projection to change the variables so that we don't have to deal with the constraints. Yeah? So we go from constrained to unconstrained optimization. And third, the resultant, the truncation effectively improves significantly the conditioning of the problem. So selecting your variables is very important when it comes to getting to the root, to the minimum quickly. Next steps, we want to put all of this on a GPU because that's going to be hopefully much faster. And potentially we have to think about the physics of those equations to further precondition the optimization. We've got 2 papers on this on arXiv. One is published on PRE. And if you search either my name or my postdoc name, you'll find them for sure. And I'm happy to take questions now.
Thank you so much. Questions?
When we wrote the sum of the periodic terms, for instance, period of the space, so how do you choose which period to look for? Or this is completely out.
Yeah, can I have the slide again? Okay, so what happens is that the frequency, yeah, it's okay. Here the numbers equal.
I recall.
Okay, so the frequency, which the frequency is also an optimization variable. So you need a guess. Yeah, so the guess, typically what we do is find near occurrences. We do numerical simulation, and then we find segments within our simulation where the 2 states are somehow close in state space.
That makes part of the fitting then? Or
Yes. Yeah, no, you have to optimize over the frequencies, but it's another optimization bit. Otherwise, there's no minimum. Because periodic orbits have a very specific period in dissipative systems. So it's not that you can choose whatever you want.
So since you mentioned distributive systems, can you try to apply, or do you think that these ideas could also successfully be applied to conservative systems?
We've got if you have a single minimum, we've got minimum on the line, you've got a family of minimum, I would say. We haven't tried because we do fluid mechanics in our department, we've got viscosity that makes the system
Because this thing about periodic coordinates also help in the morning about what's in the electric potentials, which are from the domain.
Sure.
So I can understand.
Well, we do this because our systems are very high dimensional. And the Newton-Raphson method well, does not behave very well. So if it behaves very well for your sort of lower dimensional system, then just use it.
But also there is a need.
Yeah, you go several parts.
Okay. Thank you so much. Any other questions? If not, let's take this to the And last but not least, this is from America, and the talk is a versatility method to identify chaos of other non-Hamiltonian conservative dynamical systems. Thank you. Okay, first of all, thank you for your patience to be here this time. I'm trying to be as fast as I can. We all know chaotic systems. We have many things today. Here we can see this sensitivity of the initial conditions. For example, here is the logistic map where we see that for R is for this change of the initial conditions from 10 to -6, -5, you can see this change of the trajectory. This is not an ordinary periodic regular trajectory. We might have chaotic systems as this one, where the trajectory looks like a periodic one, a regular one, but with the change of the initial condition, we have totally different trajectories. Okay, so I'm showing all this thing because to identify this chaotic behavior, we need to have some tools, and such tools are the amplifier characteristic components that we have to think about today. We have the smaller line index that Professor Scopus and Professor Woods introduced to us, the fast diagonal index that we have from Professor Longoros, right? And other. No, we talked about it. We just talked about it. You talked about it in your talk.
Yes.
You used it, but you didn't say that we used that. I said that we heard about it. And other indexes like that, grounded structures and so on. Most of these indices, as for example, the maximum number of exponent, we see that we need this W here, the variational vectors. Also, in the solid, we need the variational vectors. So, what is the main point here? That if we have a system of differential equations like this one, what's the problem? Okay, is here. We need also the variational equations, so we have double number of equations. So we need more time, more computational sources, and etc. So last year, in this conference, the 6th International Chaos and Complex Symposium was in Istanbul. I heard about this new method, the reversibility error method. It is introduced by Panici, Lotti, Kozniewski, if I'm saying bad names, and Professor Turchetti. Professor Turchetti was speaking about this last year. And it is a new method to distinguish between chaos and non-chaos, between chaos and regular behavior of dynamical systems. So, what is the common idea of REM? The common idea of REM is very simple. You take a trajectory, you integrate, then from this part you go back and see if you're going near to the initial condition, to the initial point, the trajectory is regular. If not, there is an error, so it is not regular, it is not. Okay. So this is a very simple idea. You measure this difference between the initial and the final conditions, and you see what is happening there. So it is easier because you only use the trajectories, you do not use variational vectors, so you are still working on the initial number of the differential equations. It is reliable, as they show, it is straightforward, and computationally efficient. So, there are two essential conditions for REM to work. The first one, the system must be conservative, so you can go back to the initial system, the initial conditions. And the second one is to find a numerical solver that is stable, either for forward or to backward integrations. So, most of all of the work that Tukende and his team did till now was on Hamiltonian systems because they are conservative and also they are selective. So they are okay with the two conditions. There are conservative systems and also there are easy to keep it forward and backward on time with no problems. So our idea was to extend the use of REM in conservative but not non-Hamiltonian systems, non-symplectic systems, and make this method used in many kinds of systems that we can use here. So what we did was to find a numerical solver that is not symplectic and it's good for forward and backwards way of computing the trajectory. So we checked many different numerical methods and we see that the trapezoidal method, a very simple method that you see here, can be effective for this kind of work. Here are some mathematics about the trapezoidal. I'm not going to stay here because I think that the plan is not properly enough for many details. So we use this method in the REM as a solver and try to show if it's working or not. So, some remarks first. This method, the trapezoidal method, is convergent. It appears that it works backwards and forwards. It is an implicit method. We need to use a predictor to obtain estimated solutions and a corrector. Here we use the Euler method. It is stable, as we said before. It is time symmetric, time reversible, and also it is one symplectic method. So it was a good method for us to use it to extend the REM method as we want to do. Now, what is the algorithm? You take the initial conditions, you go forward, take the conditions as initial conditions from the place where you stay there, and go back to time to the zero. And you check, as we said, the error, same problem. No. And you check the error between the initial conditions and where you go back from the backward computation. And you repeat these procedures for different time intervals. So, how you can identify counting from non-counting from the behavior of the error. In the case where the system is regular, the accumulation of numerical error stays relatively small and develops as a power law in time. So we have this kind of development of the error. If the system is chaotic, we have an increased accumulation amplifications that is relative to the maximal Lyapunov characteristic exponent. So we see this exponential growth of the error of the system. We applied REM in different systems. Here you see the method in a non-Hamiltonian, non-symplectic conservative four-dimensional system. So here you see the computations of the maximal Lyapunov exponent as we see here. This is the case, as you easily understand, of the regular orbits. You see here that the error for different times is relative to t to power a, as we expected. And here you see the chaotic behavior. The maximal Lyapunov exponent close to 1, so it is chaotic. And here you see how it goes exponentially and then stays with a big error here, as you can see. So this method works and shows very easily the chaotic behavior. We used also in three-dimensional systems. Here is the well-known Arnold Beltrami chart is the ABC flow, as they said. We can see here the same behavior. So here's the chaotic case. We see this exponential growth. It stays. You see that the error is about 100 here. It's too big. And if you go in the other case, where the system is regular, with the MLC that tends to 0, you can see this linear change of the error, and also that it stays very, very close. It's 0.0001, maybe 100 in the chaotic region, and 0.0001 here. And finally, this is another system, the spot 2 system, if you know about it. And we see also a similar behavior here. This is the regular case here, and also the case with the regular orbits. So, as what I wanted to show you is that with the use of the trapezoidal harmonic method, we can extend IM to conservative. They must be conservative, not go to non-conservative systems, but to non-Hamiltonian and non-subjective dynamic systems. And that means that we can use the method also both in odd and even dimensions for differential equations. The team that will work about this was Georgia Apostolidou from Oxford University. He has is here with us. He's student in the physics department, and also Lukas specialist from the Technical University of Dresden. Thank you very much. I hope thank you so much. Any comments, questions? I would like to ask something. So, are you able to decide the nature of the orbit faster than the other exponent? Faster not only in physical units, but also in CPU time? We didn't check it. Okay. Because we're trying to find a method. This is one thing that we must do.
Yeah, I think that
I don't think that we will have much time change, because you check it for different times and you make the computations many times. Okay, this is one point. The second thing is that, okay, you need to calculate to solve half the equation. So this is very good, yeah, of course. But I don't think that we will have significant time change.
No, but I think that it will be interesting to compare with
Yes,
other, not only the Japanese exponent, of course, but the computational math level of full, but other techniques that you mentioned that will be an interesting addition to this investigation.
and this is something that we really have to ask.
That's what I understand.
Yeah.
Came in my mind a comment many years ago. I was in a conference in Austria. There was a lady, an addition to Russia, I don't recall names. I said, if you want to translate any non-conservative system to a conservative system,
She was someone who was a technical university of Dresden. I don't remember her name, but I remember.
it was impressive. She said the Hamiltonian is, let's say, assume you have x1 and xn in your variables, and the Hamiltonian is p1 times f1, where f1 is the flow function for x1. Then p2 plus p2 times f2, and actually we take Hamilton's equation half that system. The system has double the number of variables. Then you just get each one doubles, like one. It's trivial. I wonder whether this way could fool a bit your integrator and make your method work even from the system.
So the idea is the following. Any system of differential equation can be extended in a form which is Hamiltonian, conservative Hamiltonian. And then you can apply all the techniques like symplectic integrated. Yes, the problem is that if you lose energy and you go to a point, now you can go backwards.
This is generalized.
Yeah, and it becomes generalized system and it is conservative. So in that system you do not lose energy. So in the subsystem you might lose and discuss it. This is a big point for a couple of. I don't remember her name. I was there. I don't remember her name.
Everybody's saying the amount of movement because it's very trivial.
And I still have some notes about that. That's quite interesting. Yeah, but first. That was not first. Anybody else? If not, let's stand for the session. And I hope that we will see each other later downtown office.